Hello. Okay, everyone, let's continue where we left off. All right. So now let's talk about the oxidation state for the carbon atom of each of these compounds. So we know that in general, oxygen will always be -2 um, in its compounds, and we can verify that from the guideline here. Oxygen is normally assigned oxidation state of -2. And the only exceptions is when oxygen is paired with fluorine or another oxygen molecule, and those compounds are I wouldn't say they're pretty rare, but you don't encounter them a lot. Okay, so carbon monoxide. So we just say oxygen -2. Okay, so carbon, to make it neutral, must be +2, right? Because 2 plus -2 will give us 0. Okay? All right, so now let's go with the carbon dioxide. So remember, carbon dioxide is always going to be -2 for oxygen. And then carbon, since carbon needs to have, to cancel out the oxygen's negative oxidation state, we have an oxidation state of -4. So carbon should be +4 because there are 2 oxygen atoms. So we have 2 times -2 plus 4 equals 0. All right, how about formaldehyde? So oxygen, still -2. Hydrogen in this case will be +1. And then carbon here will be, in this case, carbon, let's see here. We have 2 hydrogens, right? So carbon should be 0. So we have 2 hydrogens plus 1 plus -2. So that must mean carbon should be 0. And so in this case, carbon is 0. Okay? All right, methanol. So oxygen again, -2. Hydrogen, +1. And then carbon. In this case, if we look at the numbers here, we have 4 times +1 plus -2. So that will give us still a +2. So carbon should be -2. So we're going to say plus another -2 equals 0. So carbon should be -2 oxidation state. Okay. Now for methane, we only have carbon and oxygen. So hydrogen in this case is less electronegative than carbon. So hydrogen should have an oxidation state of +1. And then if we do our math here, carbon, since there's 4 hydrogens, it should be, it's going to be a +4 overall. So to cancel out that number, we need to make carbon -4. So in this case, carbon is -4. So we have 4 times 1 plus -4 equals 0. So the sum of the oxidation numbers should always equal the overall charge on the molecule. So for neutral molecules, they should all add up to 0. So if you do those steps, you can determine any oxidation state for any element in any chemical reaction. Okay. Now let's go on to the next thing here. So we kind of assign now many oxidation numbers, but now it kind of gets complicated when there's more than one carbon atom. So in this case, we would have to assign it for every carbon atom, and they could be different. So the carbon atoms, they don't have to be the same. So for example, like when we talked about, for example, the chromium one. So potassium chromate, there's 2 potassium atoms and chromium atoms, and there's multiple oxygen atoms, right? And we said, oh, their oxidation states are the same for each atom in the compound. Well, for carbon, that's not the case. So carbon is the one of the probably the exceptions that we'll show here. That you have to calculate it individually by looking at the atoms around each carbon atom. So let's write the formulas for ethanol and acetic acid here. So ethanol looks like this. A very important compound, not only as a for as food and drink, but also for fuel and like biodiesel, or used as a fuel alternative. So this is ethanol. It's an alcohol. It's what we refer to alcohol as a beverage, but alcohol is a very generic term for any molecule that has this OH group attached to a carbon atom. And then the oxidized version of ethanol is called acetic acid. So acetic acid has sort of a similar backbone, but you see here the second carbon atom now has lost both its hydrogen atoms, and it's been replaced with bonds of oxygen. And the OH still remains there. So this is what we call oxidation. So this is acetic acid. Okay, so when we assign oxidation numbers, the rule is this. So now imagine you're breaking the bonds so that electrons are now around the most electronegative element in the chemical bond. So if people need a refresher of what electronegative means, it's the element that attracts electrons in a chemical bond more strongly. Okay? So the trend for electronegativity, remember that the more electrons you have in the outer shell, in the valence shell, it means the higher the electronegativity. So nonmetals will typically have the higher electronegativity. So things like oxygen, fluorine. So mnemonic here we use, I think I explained it. Have no fear, have an ice, drink an ice cold beer, right? So that's the mnemonic. And if you think about it, in that case, oxygen in our examples will be the most electronegative. So pretty much the most electronegative elements we'll see are nitrogen. So nitrogen, oxygen, fluorine, and the halogens, Cl. Like that. Cl, those are pretty much the most electronegative ones. Bromine and iodine are not that electronegative, but they have electronegativity similar to carbon, which is kind of like the baseline for not having electronegative character. So carbon, it has an electronegativity, but carbon's electronegativity is higher than hydrogen. So in our case, we're going to say for electronegativity, hydrogen is less than carbon, which is less than oxygen. Okay? So in this case, oxygen is going to have the highest electronegativity. So just imagine that these bonds here, we're going to break them. So we're looking at carbon A first, right? So for ethanol, we have, let me just put an arrow here. Okay? So for ethanol, you see we broke the bonds here, and we put an electron on both carbon atoms. So that's supposed to signify that there's no electronegativity difference between two carbon atoms, so they share electrons equally. So that's a purely covalent bond there. And you see here around the carbon atom, between the hydrogen atoms here, you see we have pretty much given the carbon atoms both electrons in the bond. So we deleted the bond and gave both of those electrons to carbon. And that's because if we look here, I'm sorry, this is probably not clear enough. It looks like an arrow sign. Let's write a better C. like that. So since hydrogen has a higher electronegativity, we would say, okay, it's going to take the electrons from hydrogen because it's a higher electronegativity. And if we look at oxygen here, we gave its electrons, so see this bond that was originally here? We gave it to oxygen here. So now oxygen has all the electrons from the bonds it formed with both carbon and hydrogen. Okay? So if we look at the if we look at acetic acid, we see that we give all the double bonds are on now the oxygen atom, and then again they're shared between carbons, and here the oxygen atom takes them again. Okay, so how do we calculate the oxidation state display? Well, we use this formula where we have oxidation state A equals VA minus NA. So OX is the oxidation state of atom A, V is the number of valence electrons of atom A, and N is the number of electrons around the atom A in the oxidation state model of bonding as described in step 2. Okay, so in step 2, you look at, okay, what's more electronegative? If it's more electronegative, give the electrons to the more electronegative atom in the bond. And if they're of similar electronegativity, you're going to split them evenly, the electrons. So we look at carbon A here in ethanol. We have carbon has 4 valence electrons. So carbon is in group 4 valence electrons. And if we count around carbon A right here, we have 1, 2, 3, 4, 5 electrons around carbon A. So it'll have a -1 charge. Okay? Because it has taken because it has the electrons taken from it. It has taken the electrons from hydrogen, and so but it has 2 of its electrons taken from by oxygen, so by default it turns to -1. Okay, so we just count the electrons that we've drawn in our structure there. So now if we look at acetic acid, it's going to look drastically different, right? The same number of valence electrons, 4, but if we look at if we do look at the structure in acetic acid, we see there's only 1 electron around it, right? So there's only 1 there. All the other electrons are around oxygen. So it's 4 minus 1. So in this case, carbon has gone up in oxidation number by 4 charges or 4 places. So it's highly oxidized. So that's how we calculate oxidation numbers in organic compounds. So I can give you a simple organic compound, and I expect you to write all the oxidation numbers for every carbon atom. And then we can actually then take an average oxidation state. So we could do average oxidation state of carbon, and we could say it's going to be -1 plus 3 over 2, which gives us an oxidation state of +1. So the average oxidation state of +1. So we can calculate the average oxidation state of carbon, but we can't assign it the same oxidation state. That will not be appropriate. Oh wait, sorry. No, this is actually incorrect. Let's ignore that. Sorry. I was going off this based on if we had calculated the other oxidation state of carbon atoms. So let's just erase that for now. And I think I won't mention that. So sorry about that. Okay. So if we do calculate the oxidation state of the rest of the atoms, we will get a picture like this. Hydrogen still has +1. You could think hydrogen is +1 because it's less electronegative. The only time hydrogen is a different oxidation state is when it's in a metal, or when it's hydrogen by itself. So if you have a metal compound with hydrogen, or ionic compound with hydrogen, then hydrogen will be -1. But in this case, hydrogen is +1 because it's with other nonmetal, and usually hydrogen has the lowest electronegativity of all the nonmetals. So for our cases, we'll say it's +1 in organic compounds always. And then for the carbon here, you see there's a -3 and a -1. So in ethanol, we can average this and say, okay, the average oxidation state is going to be -1 plus -1. Okay, divided by 2. So this will turn into -4 over 2, which is an average of -2 oxidation state. So here's oxidation of, so let's go back a little bit. Okay. So oxidation of carbon equals, so it'll be an average oxidation state for carbon. So we can do an average oxidation state like that. And then for acetic acid, it'll be -3 plus 3 over 2, which gives an average of 0. Okay, so it's still the same thing kind of applies here, right? For the carbon atom with the hydrogen on it, it's a -1, and it's going to +3. And if we take the average oxidation state, we see that carbon is changing from -2 to 0, so still a net oxidation process. Okay, so let's go over in more detail how we assign these numbers. All right, so each hydrogen atom is assigned a plus oxidation state because it is less electronegative than carbon, and it only is part of one bond. Okay, I think I flipped those. Sorry, my English is really bad. So it should be, it is only part of one bond. Okay, so that sounded weird. That's because it is. Okay, the CH3 carbon atom is assigned a -3 oxidation state because it is more electronegative than hydrogen. And there are 3 hydrogen atoms bonded to it. So that's why we have -3. And then there's no contribution to the oxidation state from carbon because they have the same electronegativity, so there's no preference for electrons in that case. In that case, they'll share the electrons equally, okay? All right, so now let's talk about the important one, the one that's bonded to oxygen. So carbon's more electronegative than hydrogen, but it's more, oxygen is more electronegative than carbon. Right? So to calculate the oxidation state, we're going to assign a negative charge on carbon for every hydrogen atom is bonded to. So we have -1 times 3. And we assign a positive charge for every oxygen atom it is bonded to. So in this case, we would say it'll have 1 times +1. So in this case, we could just make this more simpler and say +1. Okay? So if we add those all up, we get an oxidation state of, let's see here, -2. So -3 plus 1 equals -2. Okay? Oh, okay. Oh, wait, no, sorry. Let's go back. There's only 2 of them, right? So if we look at this central carbon here, right here, there's only 2 hydrogen atoms. I was thinking of the other one at first. So it'll be -1 times 2 and +1. So in this case, we have -2 plus 1 equals -1. Okay, so that's much better. All right. So let's stop this video here, and we'll pick up on our discussion with acetic acid, and we'll talk about how to calculate the oxidation state there. Okay, so see you in the next video.